find the point on the plane 2x minus y plus z equal to 15 that is closest to the point 5, 3, 2. And although you could probably do this either way, we will do it using Lagrange multipliers. And before we can even do any of that, we kind of have to identify what we're trying to optimize and what our constraint is. So the idea here is that you've got some plane in space, and its equation is 2x minus y plus z equal to 15. And there's some point over here, not on the plane, 5, 3, 2. And we're trying to find the point on the plane that we don't know that is closest to that point that's not on the plane. And so in this problem, we are trying to minimize the distance between some point on the plane that we're going to find and the point out in space 5, 3, 2. So our goal here is to minimize the distance between the unknown point x, y, z and the known point 5, 3, 2. So we're trying to minimize distance equal to the square root of x minus 5 squared plus y minus 3 squared plus z minus 2 squared. We'll talk a little bit more about that in just a second. Our constraint is that the point that we're trying to find that's closest has to be on the plane. So our constraint here is that we have to have that 2x minus y plus z equals 15. Let's manipulate this just a little bit so it's a little bit more typical looking of a Lagrange multiplier situation. One thing I'll say is whenever you're trying to minimize a distance, or I suppose maximize, although almost always when you're trying to do something with distance, you're usually trying to minimize it. It is just as good to minimize the square of the distance. So what we're really going to do is we're going to try to minimize the distance squared, which we're going to write as f of x, y, z equal to x minus 5 squared plus y minus 3 squared plus z minus 2 squared. And our constraint, I'm going to write it in the typical way where we want it equal to 0, is going to be g of x, y, z equal to 2x minus y plus z minus 15, and we're going to set that equal to 0. And I don't know if Dr. Burke has talked about this or not, but it is true and very frequently done that instead of minimizing the distance of something, you minimize the distance squared. You still end up getting the same x, y, z coordinate, which is great. So we're going to do the usual thing. We're going to write our capital F of x, y, z lambda as we're using Lagrange. So f of x, y, z lambda is going to be just our usual f, little f I should say, x minus 5 squared plus y minus 3 squared plus z minus 2 squared minus lambda times our g, which is 2x minus y plus z minus 15. It's the typical set for a Lagrange multiplier situation. And then we're going to find all of our partial derivatives. In fact, why don't you find the partial derivatives? Fx, Fy, and Fz. I do not, as I've said before, I think you need to find F lambda. Maybe a minute or so to find these partial derivatives. They're not too terrible. So the partial with respect to x, the derivative of x minus 5 squared is 2 times x minus 5 to the first times 1 minus lambda times the derivative of 2x is just 2. Again, I'm not even saying the other things. I'm right. Y minus 3 squared is a constant. Z minus 2 squared is a constant as far as we're concerned for fx. For the partial with respect to y, same kind of deal. The derivative of y minus 3 squared is 2 times y minus 3 to the first times the derivative of the inside, which is also 1. And then the derivative here is minus lambda times the derivative of all that with respect to y is negative. And then thirdly, our fz is going to be 2 times z minus 2 to the first minus lambda times the derivative of that with respect to z is going to be 1. And then we're setting each of these equal to 0. So now we have the question that typically comes up is, which way do we want to go? There's kind of two ways we can go. We can either find lambda in terms of, so we can say like, we can solve each of these for lambda, or we can solve each of these for x, y, and z. I feel like it might be easier to solve for x, y, and z here. But really either way will, well, that's not always true. Most of the time either way will work, but sometimes something is easier than. So let's see what happens if we solve for x, y, and z. So here I'm going to get 2 times x minus 5 equal to 2 lambda, which means x minus 5 equals lambda, which means x equals lambda plus 5. Here I'm going to do the same sort of thing. I'm going to have 2 times y minus 3 equal to lambda. Divided by 2, I'm going to get y minus 3 equal to lambda divided by 2. And then add 3, I'm going to get y equal to lambda over 2 plus 3. And then here, same sort of thing. 2 times z minus 2. Oops, I made a small mistake there. All right, I missed the minus 1 there. So I should point out that really was a plus lambda, which means if I subtract it to both sides, it should be a minus lambda on the other side. So I should have 2 times y minus 3 equal to negative lambda, y minus 3 equal to negative lambda over 2, y equal to negative lambda over 2 plus 3. And then here, I should get 2 times z minus 2 equal to positive lambda, z equal to lambda divided by 2 plus 2. Doing those two steps at once. So these are the three things I'm then going to plug back into my constraint. Reminder, the constraint is just, the constraint's kind of generally like the thing that's limiting us, right? We're trying to find the point on the plane that's closest to this other point in space. So the point has to be on the plane, meaning that the equation of the plane, which is 2x minus y plus z equal to 15, that's our constraint. And we're going to take what x, y, and z are equal to and plug that into that equation. So we're going to get 2 times lambda plus 5 minus negative lambda over 2 plus 3 plus lambda over 2 plus 2 equal to 15. Most of the time, I would multiply both sides of this equation by 2 to get rid of the denominator. But if I take a quick look here, I see that I'm going to get a plus lambda over 2 plus another lambda over 2, and then I'll just add it to a lambda. So I don't actually need to multiply both sides by 2 to get rid of the denominators here. So let's just multiply this out. I've got 2 lambda plus 10 plus lambda over 2 minus 3 plus lambda over 2 plus 2 equal to 15. 2 lambda plus another lambda is 3 lambda. And 10 minus 3 is 7, plus 2 is 9, equals 15. So 3 lambda is equal to 15 minus 9. So lambda is equal to 2. And then lambda being 2 means that x is going to equal 2 plus 5. Y is going to equal negative 2 over 2 plus 3. So negative 1 plus 3. And z is going to equal 2 over 2 plus 2, which is 3. So the point x, 7, 2, 3 is the point on the plane that is closest to the point 5, 3, 2. Questions, comments, or mistakes I might have made. I always kind of, when I was a student, I was like, really, it works if you square the distance, and that's totally fine, and there's like no issue there. It is true, and here's why. So you don't really need to write this down or know this, but I just want you to believe that it's true. So real quickly, why is it okay to minimize or maximize the distance squared instead of just the distance? Well, think about it this way. If the distance is equal to the square root of some stuff, let's say it's some function of x, y, and z. If you take the derivative of this, that's not really great news, but it's fine. So you start taking the derivative here, it's going to be 1/2 times your stuff to the negative 1/2 times whichever partial derivative you're taking, times your del f del whatever. Let's just say it's x at the moment. And if you're setting that equal to 0 to find your critical point, you're really just setting this part equal to 0. Because what this kind of boils down to is really 1/2 times the square root of your same function times the del f del x. Well, this is never going to be 0. And even if it was, that wouldn't be helpful because we'd have division by 0. So when you're finding the critical points, you're finding them the same way you usually would, which is by setting the partial derivative that you want equal to 0. In the same sort of way here, if we were setting d squared equal to 0, d squared being just the function, right? Because we took the square root of our function and squared it. If I then take the partial derivative of d squared, oh, look, the partial derivative of this with respect to x is just del f del x. If you set that equal to 0, it's exactly the same as what you get when you set this equal to 0. So that's really the rationale behind why it's totally okay to do this. You end up getting the same critical points, whether you're setting the square root of something equal to 0 or just the inside something. It's kind of great. I should say taking the derivative, the square root of something equal to 0 or just the derivative of the thing. It works either way. It's kind of lovely. So it's totally okay to, instead of minimizing the distance squared. It'll always work out fine. So the one thing to be aware of is if they ask you what the minimum distance is, then you have to plug that point into the square root thing, not the squared thing. Because if you're trying to find the actual distance, you have to use the distance formula, which is the square root of x1 minus x2 squared plus y1 minus y2 squared plus z1 minus z2 squared. But usually they're just asking you to find the point that's closest and not asking you how far apart they are. All right. What time is it? It's 1:24. Yeah, let's start talking about double integrals. We can certainly come back and do more Lagrange or more other optimization stuff if we need to in the future, but we should start talking about double integrals. So let's go ahead and do this. Yeah. So yeah, let's start with this example. Double integrals. We're actually going to start off just with a single. So we want to, find an integral to represent the area bounded by the curves y equal to x cubed and y equal to 4x in the first quadrant. So if I was going to draw this, not that we have to draw, but I like to draw it, I would find the points of intersection. So to find the points of intersection, we're going to set the functions equal to each other. So we set x cubed equal to 4x. Again, we should always be careful here. It's not a great idea to divide by x. We're going to bring everything to one side. We get x cubed minus 4x equal to 0. We get x times x squared minus 4 equal to 0. And that ends up giving us either x equal to 0 or x equal to plus or minus 2. We don't really care about the minus 2 part because that's not in quadrant 1, but still good to know. These functions intersect each other at x equals 0 and at x equals 2 and y is 8. So it kind of looks like this. There's your y equals 4x. And here in different color, your y equals x cubed. And there's the area between them in quadrant 1. That point there is definitely the point. 2, comma 8. So if we were doing this kind of how we would do it in 16b typically, where we just want to find the area between the two curves, we would say that the area is equal to the integral from, well, actually there's two different ways we could do it. If we want to use a vertical strip, which is how I usually like to think about things, I would imagine, well, I'm integrating the top function minus the bottom function. So that's going to be 4x minus x cubed dx. And I'm thinking of that kind of as the area of my rectangle. It's my height times my base. And then my limits of integration are going to be how far left and right my vertical strip can slide. In this case, from as far left as 0 to as far right as 2. Or we could think about using a horizontal strip. And then we have to kind of change up our functions. Y equals x cubed becomes x equal to the cube root of y. And y equals 4x becomes x equal to y divided by 4, or 1/4 times y. And then we can think of our area as, well, it's still the area of a rectangle. It's still the thickness times the length. I didn't say height because effectively it's oriented kind of the wrong way to say height, but the length of the rectangle is the right function minus the left function. So it's going to be the cube root of y minus 1/4 y. That's the length of this strip here. So this horizontal strip, at the right-hand side of it is x equal to the cube root of y. The left-hand side of it is x equal to 1/4 y. And so its length is the right function minus the left function. Instead of here, the height of this strip was the top function minus the bottom function. Same sort of idea. And then our thickness is a dy, our base is a dy. So we have length. We have our base still. And then here, the strips, instead of sliding left or right, slide up and down. So this strip can slide as low as, or be drawn as low as y equals 0, and as high as y equals 8. Now, the whole thing here is that instead of writing this as a single integral, we could write both of these as double integrals. So we're going to do this again, but in a slightly different way. So we're going to write this as a double integral. So for a double integral, actually, let me say, for a single integral, we get that the area is equal to the integral from your left x value to your right x value of your top minus your bottom dx, or from your lower y value to your upper y value of your right function minus your left function dy. But now we're going to do this in a different way. We're going to say that the area is equal to the integral from x equals a to x equals b. But then we're going to say that the second integral, you're going to have y going from your bottom function to y going to your top function. We're going to have a dy dx. This double integral is the same as this single. We'll actually write it out in a second and see it. I'm just saying it is. And then I'll point out, or we can change it up and do it as y going from your low value to y going to your high value. And then x is going from your left function to your right function. A couple points of interest before we do this problem here is that the inner integral, I'm always thinking of this y matching with that y there. And the outer integral, this x is matching with that x there. Same deal if you write it the other way. This x is matching with that x there. This y is matching with this y here. So let's rewrite this area as a double integral. And I'm going to draw it again. You don't have to draw it again. We have it here. So here's my y equals 4x. Here's my x equal to the cube root. Sorry, y equal to x cubed. So if I'm thinking of this in the first kind of way with a vertical strip, so when I draw my vertical strip, well, either way, I'm thinking from the inside. I'm always working from the inner integral to the outer, because it's really the same as what we just did. So my inner integral is saying, well, I'm going from y equals the bottom function to y equals the top function. So here's how we're going to write it, which is going to feel a little bit disappointing. It's going to go from y equals x cubed to y equals 4x. But a lot of times people don't write the y equals. In fact, most of the time people don't write the y equals part. I like to think of it and say it. I think it's helpful, but people don't usually write it. So here's how this is disappointing. The y equals x cubed there, the y there that I didn't write is matching the y there. And then for my outer integral, I have x equals 0 to x equals 2. Which again, people don't usually write the x equals part. I like to write them every time. I think they're super helpful and they're not wrong to write. So it's totally fine to write this or to write the integral from x equals 0 to x equals 2, and then y equals x cubed to y equals 4x dy dx. And sometimes people, like me, like to put a 1 in there. So, right, when you integrate dy, you get y. When you integrate 1 times dy, you also get y. I just feel like it's nicer to have the 1 there, but it's not required. So let me show you what happens when we do this. When we integrate this, well, we always work from the inside out. So I do the integral from x equals 0 to x equals 2, and then the integral from y equals x cubed to y equals 4x of 1 dy dx. Well, if we're working from the inside out, I put parentheses around the inside thing. And then, great, what's the antiderivative of 1 with respect to y? Well, writing the outside stuff still. The integral of 1 is y. You're going to get y evaluated from y equals x cubed to y equals 4x. And then you're going to plug those in the usual sort of way. And you're still going to have this outer integral to work with. And then you're going to have 4x minus x cubed. And wouldn't you know it, that's exactly the same integral we wrote the first time, right? We started off by just saying, right, if you want to find the area, it's the integral from 0 to 2 of the top function minus the bottom function, the base. So that's why they're really the same. And I suppose I glossed over something important, which is that we have this idea of a partial antiderivative. Or just like with a partial derivative, whatever function you're differentiating with respect to, you treat, whatever variable you're differentiating with respect to, you treat every other variable like a constant. The same thing is true here. I'm anti-differentiating with respect to y. I'm treating anything that's not a y like a constant. And then when I anti-differentiate this constant, I get just this constant times y. And it's going to be more interesting when we have functions that have actual variables. If we wanted to finish this, it'd be just the usual process. You'd anti-differentiate this, you get 2x squared. You anti-differentiate that, you get x to the 4th over 4 from 0 to 2. You get something, you get 2 times 2 squared minus 2 to the 4th over 4 minus 0 minus 0. And you get, well, I don't know, 8 minus 4, I think. But that's not really the point. The point is that we can write it this way. So you might ask, why would you ever write the area as a double integral versus a single integral? Well, because eventually what we're going to do is we're going to have not just the area, right? We're not going to write just a 1 in there. We're going to have some function of x and y in there, which is going to represent like the height of some surface. We're going to find the volume under that surface over the region of integration. The region being some region in the xy two-dimensional plane. Okay.
We don't put in 3 dimensions, right? For double integral.
So what I would say is that we're not going to have triple integrals, but we're definitely going to have double integrals of functions of x and y that are representative of the volume under a surface. But so yes, we're dealing with 3 dimensions, but our integrals will only be integrals of 2 variables. There will never be a third variable we have to worry about. Yeah, I will also point out we could have done this one the other way using a horizontal cross section. So if we wanted to, instead of doing it the way we did it, we could have set this up as a different double integral. Yeah, we can see that, sure. We could have set this up as the double integral. So again, if I'm doing it, I'm always looking from the inside out. So my inside is going to be a dx this time, and the dy. And again, it's not because I always kind of struggle with this. I know it's a dx on the inside because I know I'm going from an x equals to left thing to an x equals a right thing, which I feel like is a little bit backwards, maybe what we used to do. So when I'm looking at this region here, which you guys you can see that right now, I'm thinking of going from x equals the left function for x equal to 1/4 y to x equals the right function, which is x equals the cube root of y. And then the y is going from as low as 0 to as high as 8. That would be an equivalent way of writing this. It would still result in the same answer of form, which I would encourage you to do on your own. It's good work. So let's look at some other stuff. It's good to be able to kind of set up the integral based on the picture. It's also good to be able to start with the double integral and sketch the region. So let's say we were given the following, integral. So we want to sketch the region of integration determined by the double integral from 0 to 3 and then from x squared to 9 of 1 times dy dx. And so when you do this, I'm going to say this lots, we always want to work from the inside out. Work from the inside out. So I can see that my inner integral is the integral from x squared to 9 of 1 times dy. So what I'm thinking here is that y is going from a low of x squared to a high of 9. So I'm going y equals x squared, y equals 9. So I'm just going to draw those functions. I'm trying to sketch the region. So y equals x squared, great. The usual parabola, parabola. And then y equals 9 is just a horizontal line. And I can also find the points of intersection, right? We know that that point there is going to be when x is 3. And this point over here is going to be when x is negative 3. And so the idea here is that if our inner integral is with a dy, that means we're thinking we have a vertical strip. Because we're thinking that the lower bound of the strip is the lower limit of integration, y equals x squared, and the upper bound is the upper limit of integration, y equals 9. And then the outer limits of integration, x equals 0 to x equals 3, tell us how far left and right we are allowed to draw the rectangle. So we can draw the rectangle as far left as x equal to 0. And as far right as x equal to 3, which means we're getting this right half of the region bounded by these two curves. We're getting all this. That's the region that this double integral is defining for us. Or in other words, if we calculated this double integral, we would get the area of that region. The part that's tricky sometimes, the part that we will often need to utilize when we deal with double integrals, is sometimes they'll give you a double integral written like this, and then there'll be either we'll be asked to, or there'll be a reason that we have to interchange the order of integration. That's something, that's probably the thing that we do the most when we're doing double, other than just double integrating to find the thing, is interchanging the order of integration. So let's do that. So we want to interchange the order of integration for the same region. And draw the region again. I'm only going to draw the region that I need here. So I just have this portion right here. I know that's y equals 9. I know that's y equals x squared. I know this line here is x equals 0. I would point out, I'm not really thinking about drawing the line x equals 3 as a boundary, because it's not that x equals 3 is really the boundary. It's that this curve and this curve are the boundaries, and we let the vertical cross-section slide as far left and right as 0 and 3. But now we want to change it up. So instead of drawing a vertical cross-section or a vertical strip, we're going to draw a horizontal cross-section. So instead of thinking of going from a low of y equals x squared to a high of y equals 9 for our inner limits of integration, now for our inner limits of integration, we're going to think of going from a left of x equals 0 to a right of this right boundary, which means we're going to have to solve for x as a function of y. So if y equals x squared, x equals, technically x equals plus or minus the square root of y. The right-hand side here is the positive side. The left-hand side here would be the x equal to the minus square root of y side. But this side here is the x equal to the positive square root of y side. So those would be my inner limits of integration, the bounds of my strip, the left bound to the right bound. And then, and that's a dx, right? The x's go with the x's. Which again, I know is not great because really if we didn't write those, we'd have y's there. So if you have y's here, you have to think, oh, it's x as a function of y, which means you have a dx. Now for the outer limits, we're going to say how low and how high can our strip be drawn. Our strip can be drawn as low as y equals 0 and as high as y equals 9. And that's going to be a dy. So this integral represents the same area, just written in the opposite order of integration. And then if you wanted to, you don't have to, but you can put a 1. If there isn't some other function in there, then the function is 1. Or said another way, whenever you do the double integral of 1, you just get the area of the region that you're describing. So why do we do this? Well, it allows us to find the volumes of solids. So, do I want to draw that picture? Not really. But I guess I will. So, let's say we want to do the following. We want to have more room on this page of paper. I guess I could just waste space, use another page of paper. Okay, so here's what we want to do. We want to find the volume of the solid in the first octant, talk about that in a second, bounded above by the plane z equal to 6 minus y, and below by the square region where x is between 0 and 2, and y is also between 0 and 2. And honestly, instead of drawing it for you, I should just show you the nice picture that is already drawn because it looks so lovely. So here is the idea of what we're doing. This top surface here is the plane z equal, it says 4, it should be 6. That's z equal to 6 minus y. And then, but we're only taking that plane above the region in the xy plane, which is bounded by x being between 0 and 2 and y being between 0 and 2. So we're saying, great, over just this square, how much volume is underneath the surface of that plane? That's what we're trying to do with the double integral that we're about to set up. Questions about anything on this picture here, or anything really at all? Good question. So it's kind of like how, you know how I draw like a little, like if we find the area under the curve, we can like draw a bunch of rectangles and find the areas of those rectangles and add them together. Well, here the idea is we can draw a bunch of columns that have a base, the little square, and the height of whatever the height is, and find the volume of each column, and then add the volumes of all those columns together to get the total volume under the surface. So I will attempt to draw this picture. It will not be lovely, but I think, oops, come on over here. There we go. So, I mean, I'm gonna.
Those are like infinitely small columns.
Exactly. Yes. The exactly the same idea. Finding the area under a curve. You've got a bunch of rectangles, and then we let all of the widths of the rectangles get narrower and narrower, so that the approximation for the area under the curve gets closer and closer to the actual area under the curve. But now instead of doing area, it's going to be volume.
Approximations of volume, like you did approximations of area.
No, but fair question. But no, the answer is typically no. So right here's our surface, which I'm okay drawing. I keep convincing myself. So here's our surface, z equal to 6 minus y. It's got an intercept here of 0, 0, 6. Got a point here of 0, 2, 6, because we've gone 2 in the x direction. That point there is 2, 0, 0. This is the x direction. This is the y direction. Same deal here. That point there is 0, 2, 0. We've got 2 in the y direction. That point there is 0, 2, 4. And this point here that point there would be 2, 2, 0. That point there is 2, 2, 4. So those are the points that are kind of the 8 corners of this volume. And then, yeah, the idea is we're taking this square in the xy plane, where x is between 0 and 2 and y is between 0 and 2. And instead of breaking it up into a bunch of little like dx's or delta x's, we're breaking it up into a bunch of dx's by dy's. So a bunch of little squares. They're not parallel. I mean, they're meant to be. So then for each little grid, for each little square, we say, okay, for this square here, the area of that square is infinitesimally like a dx by a dy. That's why we're getting the dx dy in the integral. And then the height is going to be whatever the height of the function is at that point, or approximately. It's going to be something like that. And so then we're finding the volume of that column, and then we're adding up all the volumes of the columns. So we're quote unquote adding up the volumes of the columns. Well, great. The volume of one column, I can spell column, sure, is the height of the column. Well, that's just the height of my function times the area of the base. But the area of the base is just, often people will write it as dA for a small change in area. But dA just means you can either write dx times dy or dy times dx. Either way, that makes sense to write it. So this is just your 6 minus y times dx dy, or 6 minus y times dy dx. Either way. And then we're going to quote unquote add them all up. So our total volume is going to be the double integral over the region of our function dA. That's the general way of writing it. People like, if you don't know what the region is yet, or you don't want to find the region yet. But then if we actually want to write this explicitly, we could say, well, it's going to be the integral from 0 to 2, from 0 to 2. It doesn't actually matter which one we do here because it's the same either way. Of 6 minus y dy dx. Fun fact, when all of your limits of integration are constants, or in other words, if your region of integration is a rectangle, it doesn't matter which order you do it in. And you can interchange it by just literally interchanging. So if I wanted to do dx dy instead, I would just change these to these and these to these. They have to be the same in this case. But if it was a rectangle, it was like one was 0 to 2 and the other one was like 1 to 7, you could do 0 to 2 and 1 to 7, or 1 to 7 and 0 to 2 just by changing them. There's no other work you have to do. For any other region that doesn't have the shape of a rectangle, there's more work involved in interchanging the order of integration. Like when we did the previous example here. We actually had to think about how the functions changed in our limits of integration. If they're constants, lovely, you don't have to do anything. So here, if we calculate this, so check this out. Now we're going to do the inner integral. And the inner integral, we're going to anti-differentiate with respect to the variable y. So so first write the outer one. So I still have 0 to 2. The antiderivative of 6 is 6y. The antiderivative of y is y squared over 2. And we're going to go from y equals 0 to y equals 2. We still have this dx on the outside. So then we plug in 2, subtract, plug in 0. Plugging in 2, we're going to get 6 times 2 is 12. And then 2 squared is 4 over 2 is 2. 12 minus 2 is 10. And we would just get 10 minus 0. And then the antiderivative of 10 is going to be 10x from 0 to 2. And then we plug in 2 and we plug in 0 and we get 20 minus 0, which is 20. So the volume under this surface over this square region is 20 cubic units, whatever your units happen to be.
We have to write like cubic units for not giving units.
No, not at all. No one, if someone says find the volume, they don't give a unit, you just say the volume. Done. Let's do one more. But if you need to go, you're wrong. Let's do one more where our region of integration is not so lovely. So let's say we want to find. I'm sorry. There's one more thing I want to see here. So I'll just point out. We said bounded in the first octant. Just like in 2 dimensions, the first quadrant is the quadrant where x is positive and y is positive, like the upper right quadrant. The first octant is where x is positive, y is positive, and z is positive. So where everything's positive. Unlike quadrants where they're numbered like 1, 2, 3, 4, there's like a nice order to which quadrant is which one. No one knows which quadrant is the third. Sorry, which octant is the third octant. At least not that I'm aware of. There's no like good numbering of like the first one, the second one, the third, the fourth, the fifth, sixth, seventh. It's no. You might say the 8th one was where they're all negative. I don't actually know if that's the right call though, because I would not say that personally. So you don't have to, what I really should say is you don't have to worry about it. No one's ever going to say the second or third or fifth octant. They're only going to say the first octant. You're like, great, that just means everything's positive. Okay, let's squeeze in one more example, just because I want to give you one more example. let's say we want to find the volume of the solid in the first octant bounded by x plus y plus z equal to 3, which is the plane, or what we would probably think of as z equal to 3 minus x minus y, or f of x comma y equal to 3 minus x minus y. So we're really thinking of z as a function of x and y, just like in 2 dimensions, think of y as a function of x. We can draw planes pretty easily, relatively easily, in that most planes, you can find their x, y, and z intercepts. So if I set x and y equal to 0, I'm going to get z equal to 3. If I set y and z equal to 0, I'm going to get x equal to 3. If I set x and z equal to 0, I'm going to get y equal to 3. So these 3 points define a plane. So there's a whole plane that I'm not drawing that it encompasses this triangle. And then we're trying to find the volume of this tetrahedron. So this region down here, that region in the xy plane, is the region of integration. Here's the same region drawn in 2 dimensions, where that point is the point 3, 0. That point is the point 0, 3. And so before we start integrating, we want to really find the limits of integration for our region. So I'm going to think of this using a vertical strip. And this is why we spent a couple examples practicing how to write the area as a double integral. So then we can say, oh, great. Well, for the double integral, I'm going to have y going from y equals 0 to y equals this function here, which is the function y equal to 3 minus x. And then the x limit, and that's a dy. And the x limits of integration are going to go from as far left as x equals 0 to as far right as x equals 3. And then the function that we're integrating is the height of our surface. That's our 3 minus x minus y. So that's one way we could set up this function, this double integral, to get our volume. And I guess I can stop there since it's 1:59. But that's the idea. That's what kind of makes these problems hard. It's not so much the function that we're integrating, but finding the limits of integration of the double integral. And that's why we have to be pretty good at drawing the region of integration in 2 dimensions and then figuring out how to set up the limits of integration for it so that we can then do the rest of the problem. We'll definitely talk more about this on Wednesday.